this on YouTube after today so that you guys can, I'll post the written notes so that you can see what was written down so you don't have to stress about keeping up with writing things. And then also I'll post this recording on YouTube. It'll probably be by the end of the day just because it takes a while to process big files, like movie files for YouTube, but I'll try to have it in by the end of the day. So in the last couple of days, Lisa, we're going to have our first quiz on Friday, but don't be too afraid. Okay? Be a little afraid. Just enough that you study, okay? But yes, question.
Just regarding the quiz, it's regarding I read your email when you said about today.
Yes.
About the one-dimensional.
Yes.
My question is it going to be what we covered so far, or is it going to be covering what we have learned in the homework?
So, if you've done chapter 2, Mastering Physics, which I doubt, because you guys are probably still doing chapter 1, that's fine. Since I put the due dates way at the very end, you don't have to finish chapter 1. I would jump into chapter 2 a little bit, because chapter 2 is one-dimensional motion. But to answer your question, what we do today is going to be exactly what's going to be on the quiz on Friday. And in fact, we're going to do like 3, hopefully 4, maybe 5 practice problems that are going to be exactly what you should expect to see on the quiz on Friday.
Yeah, I need a clarification because what I was noticing on the Mastering Physics is, of course, lectures is just like a way for us, like a tool to know the homework, but I was just wondering.
Like how to map, like what
there's any specifics that we learned.
Yeah. Mastering Physics is a good way to get all around practice. But I promise you guys that before every quiz, I will let you know exactly what you will expect to see on the quiz on Friday. Okay? And don't worry about it. Another thing I'll tell you now that everybody's here is that any formulas that you're going to need for the quiz on Friday, I will put them up there on the screen for you to see. You can bring any notes that you want to. And then if you want to consult with your neighbor while you're taking the quiz, that's fine. Okay? So the quiz is just an opportunity for me to see that you guys are, because I don't want to take attendance. Attendance is lame, but I want to see that you're coming and that you're comprehending what we're talking about, or at least you and your neighbor combined are comprehending what we're talking about. So we'll be all right. Okay, so let's review, unless there was another question. I thought I saw another hand. Okay. So let me go a little slower through this. So what was the whole point? The point of physics is that we want to be able to predict what objects will do as time goes by. And we're going to get into the deep water of that, which is you got to know what forces are acting on the object. And if you know what forces are acting on the object, then you can figure out the accelerations. You can do a calculation, a math equation, figure out the accelerations, and then do some kind of kinematic equations, or maybe solve differential equations to work back to find out what is the object's position at any given time. Because that's the goal of a physicist, to predict the future. And given the conditions of the universe, of the system, what will the system do as time goes by? How will it evolve? And so we're building up our language for being able to do that. And the first thing is, well, where is the particle? Where is the car? Where is the school bus? Where is the baseball? Okay, and so that's the position. Okay, we're just baby steps. The position is these blue arrows. Here's an object that's moving back and forth in the one-dimensional coordinate system. It's moving in the x direction, and the position vectors tell you where it is at any given time. The red arrows, what were those? Not position vectors, but displacement vectors. And they have the same units, their length, but they're drawn from where the object was at one particular time to where it ended at some other particular time. And so we saw that, well, that's kind of we can start to visualize the motion because the arrows are getting bigger, they're getting smaller, they're changing direction. We can see how the object kind of is moving with time, but it's not great. Maybe we could do a better job. So we said, okay, well, let's put those arrows all organized on a space versus time coordinate system instead, so that every segment of time we can draw the arrows. Okay, and then we've got change in position on the vertical axis and change in time on the horizontal axis. And we know that the slope between 2 points, the rise over the run, gives us the change between these 2 points. So since the rise over the run is the displacement vector over the time vector, this has units of meters per second. And we call this the average velocity. units of meters per second, and it's equal to the final position vector minus the initial position vector over the change in the time. And that's nice, that's a nice definition, but you can see there's issues with that because look at this table. If I wanted to write like how fast is the object going, because that's what we want to know now, we can talk about position, we also want to talk about velocity. Velocity is how fast is the object moving and in what direction. I get different answers, looking at this table here, I get different answers depending on which 2 points I use. So for example, from time 0 to 1, the displacement is 2 meters, the time is 1 second, so the velocity average is 2 meters per second. From time 0 to 2, the displacement is 4 meters and the time is 2 seconds. 4 divided by 2 is, again, it's 2 meters per second. And that lines up kind of with what we saw. We saw that, if you remember from Monday, that the object was moving at a constant speed for those first 2 seconds because its displacement was the same in the same amount of time. So it moved the same distance in the same amount of time, it must be moving the same speed. But then when we get to 3 seconds, okay, it's 5 meters divided by 3 seconds. And then when we get to 4 seconds, it's 4 meters divided by 4 seconds, that's 1 meter per second. Okay? And those purple arrows, or those purple lines, represent the slopes, those V average values, okay? But that is over the domain of 1 second, then it's over the domain of a total of 2 seconds, then it's over the domain of a total 3 seconds, and then a total 4 seconds. So you see that, like, that doesn't really tell me how fast the object is going at some moment in time. That just tells me like an average between this large amount of time. So that's not going to really help us as physicists. We want to say, where is the object at any given moment in time? And at that time, at like 35 seconds, how fast is it going? How fast is it going at that moment? In order to do that, I think you guys can see, we need those endpoints to be really close to each other. Because the closer they are to each other, the more accurate our change in position over change in time is for a moment in time. But what's that called in calculus? Bringing those points closer together. That's what the derivative is. Okay? So this is like the definition of the derivative. So someone came to office hours today and reminded me that maybe I should write this definition up here. I think this would be very helpful. That this instantaneous velocity is just the average velocity. It's the same exact thing. We just take the limit as what happens. As the t in the bottom goes to 0. So instantaneous velocity and average velocity are really the same thing, fundamentally. It's just that instantaneous velocity, which is just velocity. So from now on, when we say velocity, that's instantaneous velocity. That's how fast is that car going now, and how fast is that car going now. That's the displacement over time for a very, very small amount of time. Okay? But the only way that we can get that, to be able to take that limit, is we need enough data points. We can't just have 6 blue arrows. We need to have so many blue arrows that they fill up this entire space, not just every 10th of a second or every 100th of a second, but like millionth of a second, billionth of a second. So much so that we get a continuous function. Because you guys know from calculus, you can only take a derivative if you have a continuous function. Okay? So we need actually a recipe for what is the position as a function of time. Not just like 10 data points, or not even just 100. We need a function that tells us, like an x of t, that tells us for any given t, where is this thing? If we have that, then we can take the derivative and get the velocity. Does that kind of make that a little bit clearer? So that's where we were going for that. Yes?
Is it just like...
Raul.
Yes. Is it just always 0, or can it be like at a different point? Like
Yeah. Oh, good. Yeah. So I didn't take the time to fill up this table, but I was showing that those are the average velocities between 0 and 1 second, 0 and 2 seconds, but you could have the average velocity between 2 and 6 seconds, 2 and 5, 2 and 4, 3.5 and 3.8, 3.9 and 3 and 4, right? A derivative would be the average velocity between 4.1 and 4.10000000001. Points that are microscopically close to each other would be the same as doing a derivative. Okay. So with that under our belt, we took the idea that, okay, so if you have a position function, like a continuous function, and if you can take the derivative of that, then boom, you've got the velocity. And the units work out correctly because it's rise over run, it's meters over seconds, it's meters per second. So here's an example of something that's at rest. It's a flat line. That's what the function looks like, a flat line, a horizontal line. Because for every single time, the billions of arrows that I didn't draw, but you can imagine that they're there, all point to 4 meters. It's never not 4 meters. That's a continuous function that's derivative with respect to time, since it's got no t in it, is 0. It's a derivative of a constant. So the velocity is 0. Then here, for something that's moving at constant velocity, you just got to find out what the slope is. If you can figure out what the slope is, that's what the velocity is. Does that make sense? Okay. Negative velocity. This object has a changing velocity. What's this magical A word that says a changing velocity? Acceleration. This was a concept that was difficult for me to wrap my mind around when I was first learning physics. I'm like, I get position, I get that change in position with time as velocity, but how can you have like a change in position with respect to time with respect to time? And that's acceleration, but it's simply the change in the velocity. And as we get into two-dimensional motion, we'll realize that that's any change in a velocity. Velocity is a vector, right? That means it's an arrow. So any way that the arrow that represents velocity changes, you have acceleration. That arrow can get bigger. That means the object is doing what? If the V arrow gets bigger, what does it mean your thing's doing? It's moving faster. It's definitely moving faster. What if the V arrow is getting smaller? It's moving slower. What if the V arrow stays the same size but like goes like this? It changes its direction. In all of those cases, it's accelerating. So something that we won't say in this class is decelerating, okay? Because decelerating is a D and accelerating is an A. It's all acceleration, and it has a mathematical definition. It's dv dt, okay? Any acceleration, slowing down, speeding up, turning left, turning right, those are all accelerations. That's helpful for us. It's less confusing, okay? Anytime the velocity vector changes, change in v with respect to time, you have acceleration. And that's just one more step in the derivative chain for our graphs. So when you have something that's at rest, there's a position function for something that's at rest, a rock or this thing that's sitting here. If I want to draw a graph of this thing's velocity for all time, it's always 0. So that's why there's a line at 0 for all time for v. If I want to do the acceleration, well, the velocity is not changing. It's always 0. So the acceleration, which is the derivative of the velocity, is also 0. So it's 0. If you have something that's moving at a constant speed, there's our friend constant speed because we can see it's got a linear slope. That's the same slope for all time. That means the speed is always the same. You take the derivative of that to get the velocity, to find the slope. And there it is. You know, whatever the slope happens to be, that's what that value is. You guys said, well, somewhere above the 0. That's right, it's positive. But it's also not accelerating, right? Because the velocity is not changing. Or just think the slope of that line is 0. That means the acceleration is 0. But if you have something that's negative, something that is accelerating, it has a second derivative. It's got curvature. This thing has a velocity that's changing with time. So if we do a graph of the velocity with respect to time, it's not a flat line. It's something different that depends on the slope. It's still, the definition is still the same. It's still the slope of the position versus time graph, but it's not one slope. It's a different slope for every time you put in. So at time equals 0, it looks like the slope is 0, so the value is 0. But as the time goes on, the slope increases, so the velocity increases. But it's increasing in this case, not all cases, but in this case, it's increasing constantly. So it itself has one slope, which is the acceleration. Does that make sense? Okay, it's kind of some mental gymnastics you have to do. You're connecting derivatives to each other. Okay, and forget about going backwards. We'll go backwards and do integration in just a second. And then we did this nice example where even if you didn't know the chain rule, even if you didn't know the derivative of sine is cosine, the derivative of cosine is negative sine, that whole wheel, okay, you can find the derivatives of those functions just by doing this slope thing. So we looked at a function that could represent a mass on a spring oscillating back and forth along the x direction as time goes on. Whoop, 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 positive, negative, positive, negative. Okay, we'll talk about springs later. And if we want to know what is the velocity of that thing at any time, all we have to do is grab the values of the slopes up in the top graph. At 0, the slope is 0 because it's flat. So we put a dot at 0, et cetera, et cetera, et cetera. And we use that to draw the graph, and it turns out being a negative sine function, which is right. If you have a cosine function, the derivative is negative sine. We played the game again and said, well, what is the acceleration? It's a negative cosine. That's what we got. And then I got a question, well, what if you keep going? What if you do one more derivative? Because this thing's derivative, third derivative doesn't vanish. What's that third derivative called? Does anybody know? It's called jerk. It's just the third derivative. And would that derivative vanish too for these trig functions? No, they just keep going. So for special cases, you get higher order derivatives. And this is just interesting. There is a name for the fourth, fifth, and sixth derivative. Do you guys know of position with respect to time? Do you know what they are? Snap, crackle, and pop. I swear to God. You can look it up on Wikipedia. It's true. Okay, so that leads us to today. So the whole point of Monday was to build up this relationship that you can have in x, y, or z in any one-dimensional direction. You can have a position function. If you take the derivative of that position function with respect to time, what have you got? The velocity. You've got a function of velocity. You take the derivative, you now have a recipe for what is the velocity at any given moment. We're building up our skills as physicists, because remember, our goal as physicists is to be able to predict the future. Where will an object be at some moment in time? How fast will it be going? And how is its velocity changing? Those three things are all you need to know, or all you need to state about an object to completely describe its motion in classical mechanics. If we take the derivative of velocity with respect to time, what do we have? That's right. So that was the whole point of Monday. But we're going to use this now to derive some useful equations to help us do physics. And this is what you're going to use on Friday to answer the quiz question. So we've got, let's start here. Acceleration is given by the change in the velocity with respect to time. This is very important. For the special case, not all cases, in fact, not most cases, but for the special case when you have constant acceleration, and remember, constant acceleration means a flat line in the acceleration graph. Doesn't have to be 0, just can't have any curvature to it, okay? So that's constant acceleration. When you have constant acceleration, we can solve this little differential equation of a equals dv dt kind of easily. Okay, so let's multiply the little dt over here. So we've got a times a little change in time gives us a little change in velocity. Okay, that's a differential equation. If you're accelerating for a small amount of time, a dt, your velocity changes by a small amount. That makes sense, right? Let's integrate both sides. So the a is constant, so I'm going to take that out of this integral. And I need my limits of integration to match up because I've got equal sign. So let's integrate the time part from 0 to some final time. And let's integrate the velocity parts from the velocity at time equals 0 to the velocity at that final time. Sometimes this is called v final. And I'll take the liberty to kind of like call it v final or v of t at any given moment. What's the derivative of the, what's the integral of the left-hand side? How do you do the integral of dt? It's just t, right? That's like the integral of dx is x. The integral of dw is w. Whatever variable's in there, it just comes out. So this is a times t minus 0, right? So a times t. What's the integral of the right-hand side? It's just v, but we have to evaluate it at the limits of integration. So it's v final minus v initial. or v at the final time minus v at the initial time. So we can rearrange that, and we get acceleration is equal to v final minus v initial over t. This is our first kinematic equation. Where did that kinematic equation come from? I didn't make it up. I didn't look at it in a book and say, oh, guys, use this as a formula. Where was it? It was hiding the whole time in the definition of A is equal to dv dt. It was always there. All we did was peel it out with some mathematics. Let's keep going and peel out more from these relationships. Okay? So we've got now from this equation that v final is equal to v initial plus a times t. Okay, all that is rearranging that equation, okay? But v final is the same as v at some final time. And we know that v at some time is dx dt, or dy dt, or dz dt, whatever. It's the change in the position with respect to time in whatever direction you're working in. So this is dx dt, that's this, is equal to v initial plus a times t. So I'll play the same game. I'm going to multiply dt across the board. And then I want to integrate across the board. Is v initial a constant? It feels weird because your velocity changes, but your initial velocity is the same. It's whatever you started at. That's some number. So that's a constant. So that comes out of the integral. Acceleration is a constant for the special cases that we're doing right now, but is t a constant? No, t ticks by. 1 second, 2 seconds, 3 seconds. So t is constantly changing. So that has to stay in the integral. So let's match up our limits of integration. So we've got on the left side x initial to x final. And on the right side, our initial time, our final time, our initial time, our final time. Usually we say that the initial time is t equals 0. You could say ti, but I'm almost never going to do that going forward. So let's simplify the math now and just say we start at 0. So let's integrate. On the left-hand side, what do we have? X final minus x initial. And on the right-hand side, we have v initial times t plus a times what's here? T squared over, good. So this is our second kinematic equation. Guys, see, that's a formula there that gives you what is the position of your object if you know where it started, how fast it was going, what its acceleration was, and how long it's been doing that. So there's our recipe. It's like physics is done, okay? Well, it turns out that the universe is not constant acceleration, so it's going to get more complicated. But for now, that's it. We did it. We solved physics. Okay, we predicted where the thing is and how fast it's going. You can get 2 more nice equations from these that will be very useful for us. Let's call this equation number 3. If you plug equation number 1 into equation number 2 and get rid of t, so like if you take number 1 and solve for t, and then take that new expression and plug it into 2, you get this equation. Notice the variables that are popping up in these kinematic equations. We've got v final, we've got v initial, we've got t for time, we've got a for acceleration, we've got x of t or x final. Those mean the same thing, like final position. We've got initial position. What do you notice is useful about equation number 3? What does it not have in it? Time. So if you're trying to solve a problem and they don't give you t, and you need to find any of those other things, boom, use that equation. All of these came from the same places. They came from the dx dt equals v and dv dt equals a. So they are all valid as long as the acceleration is a constant. 9.8, 35, 0, -6. As long as it's not a changing value, as long as it's the same for the whole problem, you can use these. And then another really useful one is this, which if you plug that equation into that equation with the a, and you get rid of a, you get this guy. This. What do you notice is not in this one? Acceleration. So that's useful. If they give you a problem and they don't tell you the acceleration, you can use that. But they may not tell you the acceleration, but what do you have to know about the acceleration? Boom. Okay, so let's go. So here is a problem like the kind you'll see on Friday. Yes? I'm going to post these, but okay. While they're writing, any questions? Yes?
Okay, where'd you get the 1/2 from?
It's the integral. So when you do the integral of x dx is what? X squared over 2. Integral of t dt is t squared over 2. Yeah. Yeah, I mean, that's all. That's all. It's like the, what's it called? The antiderivative, right? You good? Yes. That one with the squares? Okay.
No,
Number 1, 2, 3, or 4?
the one is point.
Okay, yeah.
VF goes to the T, but then at the bottom it goes XF minus XI equals X of T. I'm like, how do we
Which, are you talking about this right here?
yeah.
This is this exact equation just written with the VF by itself.
But I was wondering how the VF turned into VFT.
Because, good question. Okay, so thank you. When I do these limits of integration here, this is a math thing. When you guys do integration, if you have an equality, your limits of integration need to line up with each other. Okay, they need to be equivalent for the geometry that you're integrating over. So if we're integrating from an initial time to a final time, that means we're integrating from an initial velocity to a final velocity, right? Okay. So that means that the final velocity is the same as the velocity at that time. So when I wrote v parentheses t, that's the same thing as v final. That's the velocity at the final time. So they are just the same thing. Okay. It's a notation thing. Yeah, it's just a confusing notation, but they mean the same thing. Okay. I promise you guys that doing some practice problems will clear up a lot of these questions too. Okay. So, scary looking word problem that if you were in like a math class in high school or even early college, you'd be like, what? Physics makes these easy. That's my goal as a physics teacher, is to make these things easy, not complicated. The derivations might seem complicated, but that's just kind of like to prove, look, I'm not making this stuff up. It comes from a real place. But using this stuff is super, super, super easy. Okay, so you've got an antelope that's moving with constant acceleration. That means we can use what? Kinematic equations. And it covers the distance between 2 points that are 70 meters apart. So here I have a coordinate system, like the x direction, and the antelope moves a distance between 2 points that are 70 meters apart. Okay, so what I might do is call that first point x initial, where the antelope starts, and the final point x final. Okay, and these are vectors, you know, it's like x initial 0 and x final is an arrow that points from the origin to there, but we kind of like can lose the vector thing for a little bit. As long as we remember that they can be positive or negative and that they point directions, that's good. Okay. It covers those 2 points in a time 6 seconds. Okay, so the antelope starts here. It's running, and some later time, it's here. its speed as it passes the second point is 15 meters per second. I want to draw that in there too. That's like a little velocity arrow. So when it's here, it's got a v final. The question is, what is its speed at the first point and what is its acceleration? So we don't know how fast it's going here. It's not necessarily 0, we just don't know, okay? So, strategies. How do we solve this problem? First thing I do is I write down my kinematic equations. So I've got A is equal to V final minus V initial over T. I've got X final is equal to X initial plus V initial times T plus 1/2 AT squared. I've got V final squared is equal to V initial squared plus 2A X final minus X initial. And I've got X final minus X initial over T is equal to V final plus V initial over 2. Okay? So all of those equations are correct. It just depends on which ones I want to use or which one I want to use based on what variable I'm looking for. So, strategy, try to make this easier. Here's my strategy for you guys. When you get this big problem, big word problem, first draw a picture so that you can see everything that you're dealing with and write down as many of the variables as you can. And how do you know which variables? They're all there. And there's not that many of them. There's a lot of repeats. We have X initial, X final, V initial, V final, and what else? T and acceleration. Those are the only variables that appear in those equations. And we know a lot of this information. What's X initial? We made it 0 because we drew a coordinate system and put the antelope at the beginning. What's X final? 70 meters. What's V initial? We don't know. That's what we're looking for. What's V final? 15 meters per second. What's the acceleration? We don't know. They want us to find that. What about how much time does it take to get from initial to final? 6 seconds. Okay, the game is afoot. Here are the things we know. Those are our equations. What equation should we use? Let's find V initial first. What equation should we use? Which number? Number 4. Because number 4 doesn't have A in it, and it has everything else that we already have, except for the thing that we're looking for, which is V initial. So, strategy. Draw a picture, write your equations, write down all your variables, then pick the equation you want to use, isolate the variable you're looking for. So we want V initial. So using equation 4, V initial is equal to 2 times that side minus V final, right? We use logic in physics class. We try not to memorize things. We use logic, okay? So that's what, for me, it makes this a lot easier than a math class. Okay? So now it's set up. All I have to do is plug and chug. 2 times X final is 70 meters. Minus X initial is 0 meters. Divided by 6 seconds. Minus 15 meters per second. The hardest thing about these problems is realizing that it's kinematic equations, okay? But you'll have access to your formulas because you'll have them written on your notes. But maybe like drawing a picture and like labeling what's initial and what's final. So I got 2 times 70 divided by 6 minus 15. So I get 8.3 repeating. With sig figs, what should I write? 8.33. Boom. Done. Okay, let's do the second part. What's the acceleration? Which equation should we use to find the acceleration? Yeah, whenever you can. That first one's so nice and easy. So acceleration is equal to V final minus V initial over T. So we've got 15 meters per second minus 8.33 meters per second divided by t, which is 6.00 seconds. Okay, so we've got 15 minus 8.33 divided by 6. So the acceleration is 1.11 in sig figs meters per second squared. Notice those units. Meters per second divided by seconds. Meters per second, meters per second squared. Comes out automatically. Then what I want you to be able to do, especially like on the quiz on Friday, is let's draw a picture of what the motion, or the position, the velocity, and the acceleration look like for this antelope. So we've got a position versus time graph, just a sketch. The velocity versus time graph, and the acceleration versus time graph. Okay, maybe it'll be easy to start with the one on the bottom first. What should it look like, the acceleration versus time? It should be a straight line with the value of 1.11 meters per second squared. Boom, done. 1/3 of the problem done. Does everybody see why? Okay, it's got constant acceleration. That's why we were able to use the kinematic equations. And we found that that's what the value is. What about, let's go to the position versus time graph. Where is the antelope at t equals 0? It's at 0, so it like starts here. And sometime later, in fact, at t equals 6 seconds, where is the antelope? It's at 70 meters. So this must be maybe here. This is like 70 meters. Okay, how do we connect those points though? Is this going to be a straight line? Or is it going to have some curve? It's going to have some curve. In fact, the second derivative of that curve should be 1.11 meters per second squared. You don't need to worry about that, but that's positive. It should have positive curvature. Does it start with a 0 velocity? No. We found its initial velocity. What is it? 8.33 meters per second. So this thing starts with a velocity that's not 0. And it ends with a velocity that's like 15, I think. Okay, so we know that that is a constant. Okay, my x doesn't match up, but okay, so the slope of that is 1.1 meters per second squared. So the slope at time equals 0 for the position graph should be a slope of what? No. I'll say it again. Good save. Okay, for the blue one, for the blue dude, at time equals 0 of the position versus time graph, what is the slope, what is the velocity at time equals 0? It's the 8.3. So it's got to have some positive already. It's got to have some slope to it. So it's got to already be like that. And it's curving. I didn't do a great graph. Make my dot bigger. Cheating. Okay? But it's got some curvature to it. You guys see? Okay. Let's do another one. Or think about it. Okay? It's subtle curvature, but that's okay. The antelope doesn't have a very large acceleration. It's 1.11. Free fall is 9.8. So this is like a tenth the acceleration due to gravity. Look at everything that we pulled out from this one little word problem. We used the kinematic equations, we got the missing variables, and then we were able to completely like map, like make a drawing of like what is this antelope doing with time? Like you're a biologist in the Sahara, and or savannah, not Sahara, if it's an antelope. Okay. Let's do another one. You okay? Yeah. A small block, we do more of these, it'll be better. Plus I'm filming it. A small block has constant acceleration, ding, 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 ding. as it slides down a frictionless incline. The block is released from rest at the top of the incline. So the block starts here. It's released from rest. So that means its initial velocity is 0. Its speed after it's traveled 6.8 meters is 3.8 meters per second. So once it's here, it's got a velocity equal to 3.8 meters per second. 3.80 meters per second. How far has it gone in that amount of time? It's gone a change in position of 6.8. 6.8 meters. So this is like x initial. This is like x final. Okay, what do they want us to find? How fast is the block going when it's half that distance, when it's 3.4 meters from the top of the incline? Is this going to be any different from the last problem? No. It's going to look completely different. It's like, what about antelopes and blocks on ramps? How can that be the same? It's going to be the same because the acceleration is constant. Yes?
Just a question.
Yeah.
About the block. Does it matter if we know mass?
Wonderful. So we don't need to know anything about physics yet to answer this problem. We will get to a point where we don't need to know any of this speed information. All we'll need to know are the angle of the ramp, and if there's friction, then the mass of the block. But if there's no friction, we don't even need to know the mass. But that's much later. For now, this is just a one-dimensional motion problem. You don't need to know about gravity. You don't need to know about normal forces. It's just one-dimensional motion. It looks like two, but if you tilt your head and you tilt your coordinate system, it's one dimension. So here's our coordinate system. And what do? We write down all our kinematic equations. I'm not going to write them down again, just to save time. But then after we write down the equations, what do we write down? The variables. We could have x initial, we could have x final, we could have v initial, we could have v final, we could have acceleration, and we can have time. Okay, now for this problem, they want to know how fast is it going when the block is where? Yeah, not at that point. They want to know how fast is it going halfway to that point. But I can't answer that question until I know something about this motion. What do I need to know? Wonderful. Okay, so let's use this first part to get the acceleration, which they tell us is constant, and then use that to get the thing that they're asking for. Okay, cool. So we know we're looking for A. Based on this picture, what is x initial? Yeah, I put it right on the origin. Okay? This is a location of x equals 0. What's x final for the first part? It's a 6.8 meters. What's v initial? We started at rest. What's v final? Remember, we're doing the first part where we're finding the acceleration, and then once we get that, then we'll deal with the other part. Do we know how long this takes? No problem. We don't, but no problem. Okay, so we need the acceleration. And we've got v final, v initial, x initial, and x final. Which equation should we use? The third one, because the third one doesn't have t. See the third one up there, guys? V final squared is equal to v initial squared plus 2a. Okay? All of these equations are correct. If you're now feeling stressed like, wait a minute, I don't know how he did that. I don't know how he picked that equation. Rest assured that you can pick a different equation and it's not wrong. It just might take you two equations to get to where you're getting to. Or you might go through it and be like, oh, the thing's canceled out and I didn't get what I was looking for. But none of those equations are wrong. It's just which one do you want to use to find the thing you're looking for. He cleverly says, let's use 3 because we don't know t and t's not in there. And we want a and a is in there and we know everything else. Smart cookie. Okay, so we've got v final squared is equal to v initial squared plus 2a x final minus x initial. We're looking for a, so I isolate a. Right? This, right? Check my algebra, but I think that's good. Okay, so V initial is 0, so this term will disappear. And X initial is 0, so this term will disappear. So acceleration is equal to V final squared over 2 times X final, which is 3.80 meters per second squared divided by 2 times 6.8 meters. Notice our units. Meters squared per second squared upstairs divided by meters is meters per second squared. Good, that's what we want. Plug and chug in the calculator. 3.8 squared divided by 2 times 6.8. I get 1.06 meters per second squared. No need to know about the mass, no need to know about the angle, no need to know about friction. We got the acceleration because they gave us enough information to do it. Eventually, we'll use Newton's laws, like he was asking, to actually find the acceleration right away, just from free body diagrams and Newton's laws. Okay, so now we have the acceleration. That's not what they're looking for. They're looking for how fast is the thing going when it's here. Okay, so let's go back to our list of variables and let's solve for what we really want to find, which is V final at the green place in the middle. Okay, so we can still use the same X initial. We're just going to have a different X final. The green thing is now the X final. We use the orange one. We use the orange one to get the acceleration. The acceleration is constant, so we can use the same acceleration for this whole problem. Okay, so X initial is still 0. X final is now what? Is it? It's 3.4. Good, you're with me. Okay. V initial is still, it's like the same experiment. We're just changing where we're taking the ending point. V final is what we're looking for. Acceleration we found is 1.06 meters per second squared, and we don't know the time. So don't overthink it. We want to find V final, and we have all this information. Which equation should we use? We don't have T. Third one, same exact equation we used before. Let's use the heck out of it. Okay, so but now we're looking for V final. Technically, plus or minus, just because we took the square root of both sides, okay? But our green V is pointing in our positive direction. Here we're being physicists instead of mathematicians. The green arrow for velocity is pointing in the positive direction. We'll take the positive answer. We don't always take the positive answer. Okay. So let's plug in. So V final is equal to the square root of V initial is 0, so the square root of 2 times 1.06 meters per second squared times X final minus X initial, which is 3.4 meters, because X initial is still 0. So square root of 2 times 1.06 times 3.4 is 2.68. Okay, let's do what we did last time. Make the marker a little bit bigger. Let's do position as a function of time, velocity as a function of time, and acceleration as a function of time. What's our acceleration graph going to look like? Let's do the whole motion. What's the acceleration for this problem? It's a constant value, or else we couldn't have used the kinematic equations. And it's got a value of what? 1.06 meters per second squared. Notice this, guys, and gals, everybody, that a constant acceleration does not mean a constant speed. The speed changes and changes and changes with the constant acceleration. The metaphor that I always use is like, think about boiling water on a stove. The temperature of the water, think of that as like the velocity. You put the water on the stove, you want to increase the temperature, you want to increase the velocity. So you turn on the flame. The flame is like the acceleration. You just turn on the flame and you leave the flame on, and the water gets hotter and hotter and hotter and hotter with a constant flame. So acceleration is like the flame that's propelling your system, causing the change in the velocity. A constant value just means it's on. A constant positive value that's not zero means that it's on. So that means your velocity is going to change, get bigger and bigger and bigger, or more positive. Okay, so yeah, that's a positive value at 1.06. This is in meters per second squared. This is t, this is t. Okay, what about the position as a function of time graph? What's that going to look like? Is it going to be straight? It's going to curve. Okay, so we've got some positions. We've got x equals 0. These are our positions. We've got x equals 3.4 meters. And we've got x equals 6.8. Okay, so 6.8 is twice as far away from 0 as 3.4. But are we going twice as fast? No, because these things are like quadratic. It doesn't change like double, like linearly like that, okay? So we know that it's going to make a shape that looks like this, and we start at 0. Velocity equals 0, so the slope is 0. So something like this. So when we're at this position, it's this time. When we're at this position, it's this time. Okay, so how fast are we going? How fast are we going at 0? We're going 0. How fast are we going at this time? When we're at 3.4, how fast? 2.68, good. So this is 2.68. These are in meters per second. And how fast are we going at this time? 3.8. That was what we started at. At the beginning of the problem. This is important, okay? 3.8. So 3.8 is not twice 2.68. It's less than twice. It's like here. So that's what our velocity versus time graph looks like. Okay, so here's what, guys. I tell you what. So we ran out of time, but don't leave and don't pack up for just a second because I want you to hear this. The problem that we're going to do for the quiz is going to be very similar to this one right here, 2.36, okay? So what I'm going to do on Friday is we'll do this one together before the quiz. That's helpful, right? Okay? And then you'll do the quiz with a problem like this, but I might ask you for some different things. So I'll lecture a little bit at the beginning of Friday, and then you'll do the quiz. But I'll post these notes. Much better, right? Okay, good.